let's start with a warm-up problem to avoid getting any mental cramps as we learn new things. So this is a problem that hopefully, if you understood what we did in the last video, you can kind of understand what we're about to do right now. And I'm going to escalate it even more. In the last video, we finished with a 4-digit number times a 1-digit number. Let's up the stakes to a 5-digit number. So let's do 64,329 times, let me think of a nice number, times 4. I'm going to show you right now that we're going to do the exact same process that we did in the last video. We just have to do it a little bit longer than we did before. So we just start off saying, OK, what's 4 times 9? 4 times 9 is equal to 36. Right? 18 times 2, yep, 36. So we write the 6 down here. Carry the 3 up there. Just put the 3 up there. Then you got 4 times 2. 4 times 2. 4 times 2. And then you're going to have to add the 3. So let me just write that there. Plus 3 is equal to, you do the multiplication first. So you can even think of it as an order of operations. But you just should know that you do the multiplication first. So it's 8 plus, so 4 times 2 is 8, plus 3 is equal to 11. Put this one down here and put the 110 and 11 up there. Then you got 4 times 3. 4 times 3. 4 times 3. You got that one up there, so you're going to have to add that plus 1 is equal to, that's going to equal 12 plus 1, which is equal to 13. So it's 13. Then you have 4 times 4. 4 times 4. You have this little 1 hanging out here from the previous multiplication, so you're going to have to add that. And that's equal to 16 plus 1. It's equal to 17. Stick the 7 down here. Put the 1 up there. We're almost done. Almost done. And then we have 4 times 6. 4 times 6 plus 1. Plus 1. What is that? 4 times 6 is 24, plus 1 is 25. Put the 5 down here. There's nowhere to put the 2. There's no more multiplications to do, so we just put the 2 down there. So 64,329 times 4 is 257,316. And in case you're wondering, these commas don't mean much. They just help me read the number. So I put it after every 3 digits, so I know that, for example, that everything after this, these are in the thousands. So this is 7,000. If I had another comma here, then I know this is millions. So it just helps me read the problem a bit. But if most people were to see, let me draw a tree here. So that's a twig right over there. Maybe I'll draw some leaves. So if most people, so that is, and let me draw the apple over here. So this is the apple right over here. So for most people, if I were to kind of snap this twig right over here, it's completely common sense. The apple would fall. And if most people were to observe it, they would just think it's a normal happening in the universe. But for Isaac Newton, at least on that day when he observed that apple, he says, well, why did that apple fall? And this, to some degree, is a great example of out-of-box thinking. Because something that for thousands of years, or tens of thousands of years, human beings had taken for granted, just because that's the way it always was, he actually asked the question, why? Does it always have to be that way? And that question took him down an entire line of reasoning that set up the basis for all of classical mechanics, which for the most part we still use today. It's been tweaked a good bit by this gentleman in the last 100 years. But for most purposes, when we're engineering things or dealing with things on the surface of the planet, and we're not going close to the speed of light, we can still use the mathematics that Isaac Newton came up with from this simple question. And not only was he able to kind of think that there's something that might be pulling, somehow acting on this apple, bringing it to the earth, but he actually formulated an entire, I guess, law around this thing. So as you can imagine, the thing that Isaac Newton believes brought the apple to the earth is gravity. is gravity. And he formulated the universal law of gravitation, or the law of universal gravitation, either way. And in it, he theorizes that the force between two objects, and it's a vector quantity, it's always going to attract the two objects to each other. So the direction is towards each other. The force of gravity between two objects is going to be equal to this big G, which is really just a number. It's a number, and we'll see in a second that it's a very small number. Maybe I'll write it there. This is a small number. I'll give you that number in a second. It's equal to this constant, this universal gravitational constant, which is a super duper small number, times the mass of the first object times the mass of the second object divided by the distance between the two objects, the distance squared. So this is distance between both of those two objects. So if you're talking about the force of gravity on Earth, this right over here, you'd pick one of the masses to be Earth. So this mass over here, if you were talking about on Earth, you'd pick one of them to be Earth. This is the object that's on Earth. Maybe it's me. And then this is the distance between the center of masses of both of those objects. So between the center of me, and I won't go into the detail of that, I'll make a more detailed video on center of masses, and the center of the Earth. So it's roughly the distance from the surface of the Earth, or if I'm about 5'9", about half of that distance of, I guess the distance from my belly button about to the center of the Earth is this number right over here. So right when you see this, before we even talk about me and an Earth, or needles and Earth, or taxi cabs and Earth and that force of gravity, something bizarre might be raising up in your brain. You might say, wait, the way gravity is defined by Isaac Newton, or this formula that we're given right here, it's saying that we have gravity between any two objects. And you're saying, look, I'm looking at a computer screen right now. So you're looking at a computer screen right now. And let me take my best attempt at drawing well, this is an old school computer, not a flat panel, but gets the job across. So you're looking at a computer screen right now. How come you aren't attracted to the computer screen? How come it doesn't fly into your face? And the answer there is that this number is really small. And there actually is some force of attraction between you and the computer. It's just that it's more than overcompensated for the friction between the computer and the desk, the friction between you and your seat, and which is frankly being caused by the force between you and the Earth, the force of gravitation between the computer and the Earth. That both of you and the computer are such small masses that you really can't notice it. It's really negligible, and it's being overpowered by other forces that are keeping the computer from even drifting into your face, or your face drifting into the computer.
The present tense is how we talk about things that are happening in the present moment. Like, I eat a donut. If I say that, if I say it that way, it means it's happening right now, in the present, as opposed to happening later, in the future, or before now, in the past. The present tense is what's happening right now. If you can just imagine, just put the words right now at the end of anything that takes place in the present. It should work. I eat a donut right now. Louise doesn't want a catapult right now. The water is super cold right now. Bertie is singing in the shower right now. All of these sentences are taking place in what we call the present. There are a couple of ways to form the present tense, and I've demonstrated two of them here. So we can say, eat, or doesn't, or is, but we can also say is singing. So when you generally have something that has is and ing in it, it means it's happening right now. It's happening in the present tense. So yeah, those are two of the ways to form the present. Is if the verb is, kind of unadorned, if it's kind of plain, I eat a donut, not I was eating a donut, or I ate a donut, or I will eat a donut, just I eat a donut. If it's just sort of on its own, like this, it's probably going to be in the present tense. Likewise, if you see the word is and then ing, that also means it's in the present tense. That's what you got to know about the present tense. It's happening now. You can learn anything. David out.